So, first thing I want to tell you, what is the question I'm looking at? So it starts harmless enough, always looking at a ring R with unit, so that's always in the background, will never change. And then I have a bounded chain complex of projective R modules. The thing is any projective module, so not finitely generated. I mean, in some sense, that's the whole point here. So because I want to look at a particular finiteness condition of this chain complex, this complex is called R finitely dominated. If C is a retract up to homotopy of a bounded chain complex of finitely generated free R modules. Okay, the free here is of course important. So in other words, I find these maps S and R, and before I find those, I find the complex D, which is bounded, finitely generated free over R, such that R composed with S is homotopic to the identity, right? Not equal, but homotopic. And this is just a definition. So what I did not put on the slide is the motivation. I mean, this is a notion that has been studied, for example, in group theory. So the question is phrased usually with different letters and words, like, is this group of type FP? That's very much this question. If you're interested in like finiteness properties of topological spaces, this is the algebraic version of that. So it does connect to other things. But I'm essentially looking at that just from the point of view of homological algebra here. And I thought it might be helpful to see a few other characterizations, two more precisely. First of all, C is R finitely dominated. That is the same as saying that C is a retract, and now I really mean a strict retract, meaning a direct summand, of a chain complex which is homotopy equivalent to a bounded complex of finitely generated free R modules. Okay, so you can kind of play off, okay, here I have it's homotopic to the identity. You can say, well, this is actually equal. It's a retract of some complex D, but then D isn't finitely generated free. It's only homotopy equivalent to something finitely generated free. This is relatively easy to prove. Much more difficult to show is the last characterization. That's the same as saying that C is homotopy equivalent to a bounded chain complex of finitely generated projective modules. So that's a result of Andrew Wranitzky in 1985. Right, so that's the basic definition. This is what I want to talk about. And more precisely, I want to look at a special case. Namely, I look at the ring Ln, which is a Lohrmann polynomial ring over R in n indeterminates. Right? So I have x1 up to xn and their inverses. And I look at a bounded complex of finitely generated free Ln modules. And Ln as an R module is not finite, right? That's infinitely generated. So it's a priori not clear that such a complex C satisfies any reasonable finiteness condition over R. Okay, if you forget about all the Lohrmann variables, just think of that as a complex of R modules, you lose finiteness immediately. So the question I want to address can be characterized whether C is R finitely dominated, or more precisely, is there a homological characterization for finite domination? And the good news is, here's the answer, yes. Okay, but I'll be a little bit more specific in a while. So in fact, the result I'm going to talk about, I've advertised that for quite some while. So I introduced a novelty in this talk. I'll actually state the result in full generality. Okay, so but that requires, unfortunately, some build-up. So before I substantiate this yes a little bit, we need to look at some, well, combinatorial constructions. So something apparently completely different first. I want to tell you how to get rings from cones. Okay, so everybody who has seen Toric varieties, and that should be everybody here, of course knows the beginning. I think of the Lohrmann polynomial ring. That's the group ring of Zn, right? Group ring of the integral lattice. I want to think of that as functions from Zn into the ring R with finite support. Okay, that's pretty standard. And then if you have an n-dimensional rational polyhedral cone, sigma, so sigma is the positive span of a finite bunch of vectors. All these vectors are in Zn, right? So the first thing is the polyhedral cone. The second condition here that the Vj can be chosen integral, that's the rationality. And I want a span of sigma, meaning the span of these vectors, to be all of Rn. So that's an n-dimensional polyhedral cone, and that determines a subring of Ln. Namely, I just look at those functions from Zn to R whose support lie in sigma. Okay, so as I say, this is totally standard and familiar. If sigma is the first quadrant in R2, you just get a polynomial ring in two variables. If sigma is the upper half plane, right, that's also allowed, doesn't have a vertex, but who cares? Then you get like R of x1, x1 inverse, x2. These are rings kind of in the background of this whole game. But we can construct a few more rings, kind of more interesting ones. So if we have one of these sigmas, which in addition does not contain a line, so now I don't want anything like the upper half plane, I really want the thing to have a vertex, meaning sigma is pointed, then I can look at functions from Zn to R as before, whose support is in sigma, but I don't insist on having finite support, right? So I forget about the finiteness. So this is then well, denoted by this R double square brackets, because this is something like a power series ring, formal power series ring. Right? And I can vary that a little bit. Well, that's what I call the Novikov ring, determined by the cone sigma. That is, well, pretty much the same. You look at functions from Zn to R. Now, you don't want the support to be in sigma. You want the support to be a set such that if you shift finitely often in a direction, then the support ends up inside sigma. All right, and the shift, that's this kw, so k is just some number that tells you how often you're allowed to shift in direction w, and w is just any vector you choose in the interior of your cone sigma. Okay, it doesn't matter which one you choose, you always get the same definition in that way. So that's the Novikov ring determined by sigma. Examples in one dimension, if sigma is the positive half line, then of course R of sigma with single square brackets, that's just polynomial ring in one variable. That's the usual toric ring. The double square brackets thing is then just formal power series in this one variable x. Right? I mean, support in the positive half line, no finiteness condition. This funny Novikov construction tells you you have support somewhere in Z, but if you shift finitely often in the positive direction, you end up in the first half line. So that's precisely what is usually called the Novikov ring R of double parenthesis this x. This is a localization of the power series ring by x. So it's formal power series which have finitely many negative exponents of x appearing, but possibly infinitely many positive exponents. Okay, so these are nice rings you get in general for pointed cones. Unfortunately, we need that also for cones that do contain a line. So what do we do then? Essentially, we factor out the cospan of the cone. So the cospan of sigma, that's the largest vector space contained in sigma. And then we pass to the quotient in Rn divided by this cospan. Okay, and again, this is a construction familiar from toric geometry. I have the image L bar, that's the image of Zn in this quotient that is still a lattice. Sigma bar is the image of the cone in that quotient. And now the thing is, of course, that sigma bar is actually a pointed polyhedral cone in that quotient, and it is rational with respect to this image lattice L bar. Okay? Once again, this is all standard. But now we can essentially apply the definition for the pointed cone, but not over the ring R. I take the group ring of, well, the integral points in the cospan of sigma. Okay, so R of Zn intersection cospan of sigma, that's a sublattice of Zn. So in other words, now I don't work over R, I work over some Laurent polynomial ring, okay, and apply the exact same construction to sigma bar over this bigger ground ring. So explicitly, if you look at sigma upper half plane in R2, this is an unpointed cone, then the cospan is just the x-axis, right? That's the largest vector space contained in there. Then this R of Z2 intersection cospan, this is just a Laurent polynomial ring in x1 only, in the first variable. So the Novikov ring that determines is then the Novikov ring in X2, so formal Laurent power series, versus finite many negative exponents of X2, but the coefficients are allowed in the Laurent polynomial ring in X1. Right? So that's a game we can play. And to make it plausible that this is actually useful, here's the result. Okay, so this is joint work with David Quinn. And the result reads like that. If you have a bounded chain complex, finitely generated modules over Ln, right? That's the Laurent polynomial ring in n indeterminates. And you have an n-dimensional lattice polytope P given somewhere in the background. And then it turns out that this C, the complex, is R finitely dominated if and only for every phase f of P some homological condition is satisfied. So that tells you if you tensor C up to one of these Novikov rings, the thing becomes contractible. I mean, that's sometimes said like the Novikov homology vanishes, but then you have to specify with what coefficients. Right, so this is a Novikov ring of a cone sigma f, which is associated to the phase f of the polytope. All right, this is just, well, the barrier cone of the phase. So, I mean, choose your point in the phase, in the relative interior of the phase, and then you take the cone of generated by everything which points from that point to somewhere in the polytope. Yes, please. Good question, and the answer is nothing. That's exactly the point. Right? So this is not just one theorem, as Graham just observed. These are infinitely many theorems. Maybe I shouldn't state that as one and just keep going through a slide. Okay, for each P, each integral lattice polytope of dimension n gives you a new characterization of finite domination. Right? So what I'm trying to do is I'm trying to explain at least the idea of this proof, but not in full generality. I will actually restrict to the case n equals 1. Which is in fact also the motivating case, and then I will comment a bit later of what changes. Right, but this is, and oh, I should also say I only talk about the if direction. This is why I put the if in parentheses. The reason is not, I mean, we can prove both directions, but it's the if direction that is nice and conceptual. The only if direction is not so nice. Yes. The 10 seconds I used up by pushing the button so off. Sorry. There it is. Okay, you forget about the Laurent structure and just look at that as modules over the ground ring. Okay, I mean, Wronitzky's characterization is the easiest. You want that thing to be essentially to consist of finitely generated projective modules up to homotopy. Right? Okay. Right, so here's the theorem in its full beauty. Now, the next slide should show the motivating case n equals 1. Okay, for n equals 1, there's only one theorem because you don't have that many polytopes in dimension 1. Right? So you can just as well restrict to the unit interval. The Novikov rings here are, well, just what I said before, formal Laurent power series ring with finitely many negative exponents of either x or x inverse, depending on which end of the polytope you're looking at. Okay, both of them contain L1. Of course, both contain the Laurent polynomial ring. And then Wronitzky has shown in 1995, and that's the theorem that really got me into the subject. If you have a bounded complex of finitely generated free L1 modules, then the C is finitely dominated if and only if C has trivial Novikov homology. So if you tensor up with Novikov ring R of X, and the Novikov ring R of X inverse, in both cases you get something that's acyclic or contractible. That's the same in view of all the freeness here. Okay, so this is really the one-dimensional case of the theorem. Okay, so how would you go about proving that? Right, so what I'm going to do is I'll give you Wronitzky's proof in words that he would not approve of, and then point out why this rephrasing is good, because it tells you how to do that for general n. So the strategy is I speak algebraic geometry, but I write homological algebra. So it's one of my hobbies to pretend that I'm algebraic geometer. I mean, every so often that gets me into trouble, but okay, let's ignore that. So in this case, that works like that. I think of the ring Ln as an algebraic n-torus. I should probably say spectrum of Ln, and then I should also say let R be a commutative ring. But this is philosophy, right? This is not algebraic geometry, this is just philosophy. So think of Ln as an algebraic torus. A complex of finitely generated free Ln modules is actually a complex of trivial vector bundles on this torus. Okay, so what you then do is you first of all choose a suitable toric compactification x of t. Suitable is a bit misleading. Suitable means any. Well, projective or something, right? But that's the choice of the polytope p, of course. Right, then extend the complex C, which are trivial vector bundles on the torus, extend that to all of x. Then you reinterpret this condition that the Novikov homology of the complex C vanishes. This is something like being homologically trivial on a formal or infinitesimal neighborhood of the complement of the torus in X. And then you have to compare what would be sheaf cohomology in algebraic geometry in different topologies. So this is Zariski and FPQC to get the result. Okay, so you will notice that my algebraic geometry becomes more and more fuzzy as we progress through the proof. Okay, so here's the first step in the proof, n equals 1, right? So you have this bounded complex of finitely generated free L1 modules, and then there's a nice proposition originally due to, well, Wronitsky, that's where I learned about that at least. So then you find bounded chain complexes C plus and C minus of finitely generated free modules, but now over the polynomial rings, R of X inverse, together with a diagram like this, okay, C in the middle, C plus, C minus on the right. The maps are as linear as possible, and that satisfies three kind of conditions that might look a little bit mysterious at first. The first condition, kind of an isomorphism condition, tells you that you can actually reconstruct C from C minus and from C plus, right? So if you tensor C plus over R of X with the full Laurent polynomial ring, you get precisely what you had before, namely the C, and the same on the other side. Okay, the second condition says that if you take the limit of this diagram in each chain level, okay, that's nothing fancy, just in each chain level take the pullback, you get a finitely generated free R module. And the third condition is if you take in each chain level higher derived inverse limits, you get nothing. Right? So that comes from Wronitsky's paper. That's kind of the algebraic version of what he calls algebraic transversality. Okay, now let's do the pretend game. We're all algebraic geometers. So we have our bounded complex of trivial vector bundles on an algebraic torus, spectrum of L1. Now this is P1 with 2 points removed, namely 0 and infinity. Okay, you think of P1 as the spectrum of, as a union of two spectra of polynomial rings, right? As a union of two affine lines, and the union is along the algebraic torus. So you can see the three rings already appearing here. And then what algebraic transversality really says is that C extends to a complex of sheaves on the projective line, such that, first of all, this new complex, that's an S. It looks like a C, but it's actually an S. Right, so S is quasi-coherent. That's the first condition. That's this isomorphism condition from the previous slide. The second condition was something about the pullback, the limit. Okay, so that translates into global sections. I want those to be finitely generated free over R. And the third condition on the higher inverse limit, that translates into there being no higher sheaf cohomology. Again, that's in each chain level, right? I mean, algebraic geometers find that trivial. The good news is that you can do that explicitly, meaning also over non-commutative rings, because what you see in each chain level is a direct sum of diagrams of this type, where you really have things, well, free of rank 1 in as much rank makes sense, and then such that these parameters A and B sum up to something positive, so in other words, ample line bundles, and then you can actually compute these pullbacks and the high derived inverse limits explicitly using check cohomology, essentially. Yes, please.
C or S?
Yeah, as I said, it looks like a C, but it actually is an S. That's a misprint. Yeah, that should be an S here. Right? The extension is quasi-coherent. Okay, it can be done purely combinatorially, explicitly, but think of it in these algebraic geometric terms rather. Okay, so Why do we want this condition that there's no higher sheaf cohomology? Well, the reason is that then I can compare, well, global sections of S level-wise in each chain level with what is usually called hypercohomology, which homotopy theorists would call the homotopy limit of this diagram as I just constructed before. So this homotopy limit or hypercohomology, that's just the totalization of the check complex. In other words, you look at the mapping cone of this type of diagram here. Right? That's really check cohomology for P1. Right? Hypercohomology is just hyper fancy terminology for precisely this. And because of this lim1 condition being 0, that is the same up to homotopy equivalence, right? It's the same. Now comes this step that I pass to a different topology. I mean, so far I was always speaking Zariski, even though I didn't say that. Now I want to replace this Zariski covering of P1 by an FPQC covering. At least I think these are the correct 4 letters. Now, what is that? Well, first of all, I still take the torus, the spectrum of L1, that is still there. Okay, and then I look at the spectrum of the power series ring in X. Okay, this is like an infinitesimal neighborhood of the point 0 in the projective line. Okay, and these two, of course, intersect, namely in the spectrum of the Novikov ring, which is precisely an infinitesimal neighborhood of the point 0 without the point 0. Okay, so this is one of these things where you can talk about a neighborhood of something that isn't even there. That's precisely the spectrum. And of course, what you can do to 0, you can do to infinity as well. So you have the point infinity, or rather an infinitesimal neighborhood at the other end, and the intersection with the torus, then the spectrum of another Novikov ring. Okay, so at least you can see the Novikov rings appearing that show up in the theorem. Okay, and then we have to use the fact that if you construct hypercohomology with either the Zariski covering or with the FPQC covering, that's the same. Right, here's where my algebraic geometry is really fuzzy. For me, this is just a statement, write down 2 different chain complexes, right, which are, I mean, totalizations of check type complexes, and show that they have homotopy equivalent totalizations, which is not particularly difficult in this case. Right? If you do that slightly more combinatorially on the algebraic side, that means that you replace this diagram S, which had 3 entries, by a bigger diagram B, such that the homotopy limit of S and the homotopy limit of B, which is like hypercohomology in the FPQC topology, okay, that these are the same up to homotopy. Right? So the bigger diagram looks like this. It has 5 entries. And I mean, here again, you see the power series rings appearing, you see the Novikov rings appearing, and you reassuringly still have the original complex C in the middle, which is good because we want to show something about C. Right? So we can all do that. The question is this a good idea? Okay, and here's why it is a good idea. So not this one line alone, but you can certainly look at one of the entries in the diagram was this C minus tensor over a polynomial ring with one of the Novikov rings. Okay, write that in a more complicated way. That's what you usually do in math if you're stuck. Right? Instead of tensoring up to the Novikov ring all in one step, tensor up to the Laurent polynomial ring first. Okay, that's the same always. But now by algebraic transversality, what I've written in red up there, C minus tensor over the polynomial ring with the Laurent polynomial ring, that's precisely our C. Right? So what you really see is C tensor over L1 with the Novikov ring, but that's what the theorem tells us, I mean the hypotheses tell us rather, this is actually 0, or more precisely contractible by hypothesis. Okay, so that was the picture at infinity. The same goes for the other side at 0. And because hypercohomology is hyperhomotopy invariant, that tells us, sorry, I should say homotopy invariant, that means we can actually replace these entries in the bigger diagram, which I've just analyzed, by zeros, okay, because they're contractible. I can just replace them by honest zeros, and I still get the same up to homotopy in the homotopy limit. Okay, and why is that useful? Because the homotopy limit is just a totalization of a check complex of that, but the totalization of a check complex is just a direct sum of these 2 entries, because they don't map to each other anymore, right? I've just put zeros in the middle. Okay, Okay, so in other words, I get a junk term, I get the C, which I want, and I get another junk term. So this C in the middle, this is a direct summand of, and now I just go backwards through the proof of the homotopy limit of this B prime, same as the homotopy limit of B, which is the same as the homotopy limit of S, which is the same as the limit of S, okay, global sections of S. But that was by construction bounded, finitely generated free over R. Okay, so by one of the many characterizations of finite domination, it tells us that C is R finitely dominated. Right. As I say, this isn't original, this is really Wronitsky's proof. Just if you read Wronitsky's paper, it might be hard to recognize that as the same at first. Right? So the good news is that this type of proof with the exact same arguments, that generalizes to arbitrary n and p. Okay, so p is an n-dimensional lattice polytope. I should probably have said simple, in fact. I forgot that. So in terms of combinatorics, these small diagrams, okay, these corresponding to the Zariski covariance, they're indexed by the phase lattice of P. I mean, that's again the usual thing you expect from toric geometry. The big diagrams, after passage to FPQC topology, they would then be indexed by the phase lattice of the barycentric subdivision of P. So in other words, if you go to high dimensions, that gets a little bit of a nuisance to write down, because the diagrams blow up in size pretty fast. Okay, but if you then go through the proof, I mean, you extend, you change to topology, to FPQC topology and so on. You modify the big diagram by putting zeros at the appropriate places, and what you end up with is we'll still have the complex C bang in the center, okay, and will be surrounded by zeros. That's basically coming from the hypotheses. And then you have stuff along the boundary. That's what I called junk terms before, right? The whole point is you isolate C from all the junk along the boundary of the polytope. Okay, so in other words, if you go to the homotopy limit of that kind of diagram, C will still be a direct summand of the whole thing. And in other words, it's really the exact same arguments, it's just that the bookkeeping becomes quite a bit more demanding. Right, so that is the strategy of the proof in general. What I plan to do now is to give you a special case of the theorem, not n equals 1, because you've seen that. So just to give you the impression that one can actually write this down explicitly. So if we look at two variables and then choose x to be p1 times p1, this is really the simplest case for notational purposes. Okay, a nice square, that's the, that will be the polytope. So in this case, a square has 8 faces, I guess, okay, not counting the square itself. So you will get 8 homological conditions. Okay, so I mean, this is kind of from older presentations where the 8 came as a surprise. So one of the conditions look like that. You take C and you tensor over the Laurent polynomial ring in 2 variables with Novikov ring in X over a Laurent polynomial ring in Y. Sorry, I switched to X and Y here rather than X1, X2. And that should be acyclic, and then you get 4 more conditions. These are the conditions that come from the edges of the square. P is a square. And then you get 4 other conditions coming from the vertices. And here you have this kind of new type of Novikov ring appearing, right, that is our double parenthesis xy. So this is formal power series in x and y, and then you invert the product xy. Okay, so if that's exactly the thing in terms of support. You look at maps from Z2 into R such that the support can be shifted. If you shift to the top right finitely often, then you end up in the first quadrant. Okay, so that comes from one of the vertices, and then of course you have the other 3 vertices. And that is a complete homological characterization of R finite domination in this case. One thing I really should say, it's very tempting to think that why do I make all this fuss? Why don't you just iterate? Okay, I mean, a Laurent polynomial ring in 2 variables is a Laurent polynomial ring in 1 variable over another Laurent polynomial ring in 1 variable. Okay, and if you do that, then you would certainly get, for example, the first 2 conditions, right, just by applying Wronitsky's original theorem once. And then you're stuck, because Wranitzky's original theorem explicitly started off with 3 modules over the Laurent polynomial ring. Okay, what you get out is something which is finitely dominated, meaning basically consists of projective modules. And that is, in terms of the proof, an actual obstacle. Okay, I mean, the first step was to extend something. If you don't start with 3, you can't extend. There's a k-theoretical obstruction. The funny thing is you can circumvent that problem. You can make the iteration work, but it's kind of ugly. This is nicer. Right? So, okay, once you have an explicit characterization for n equals 2, I thought I should stop with an explicit example here. So let's say Z is our ground ring. I have a Laurent polynomial ring, 2 variables. Now I fix these 2 nice looking elements, mu and nu. And then I look at this chain complex here, L2 mapping to L2 plus L2 mapping to L2. Maps are given by that matrix. And this is actually, I mean, this is not surprising if you don't think about it. But if you do think about it, actually is a little bit surprising. That thing is, in fact, Z finitely dominated. And the way why this is relatively easy to check with our theorem is that this complex actually is the totalization of a double complex, which is just a square. And these mu and nu respectively become units, each of them in 4 of the Novikov rings that are involved, but in 4 different ones. You know, 4 here, 4 there. Together you cover all the 8 cases. So the theorem gives you finite domination of this quite easily. That, of course, essentially means you can look at the Newton polytopes of mu and nu and get the results. So my hope would be, if you look at examples like that, you can actually construct a suitable polytope P from these Newton polytopes. But I don't have an algorithm for that. All right, that's what I wanted to say. Thank you.